to start with an example here that's going to have us look at conservation of energy. And it's going to help us to kind of think through and visualize how work is related to energy and how conservation of energy is done. So when we actually do this, I'm going to use this example. And this is a conceptual example. We've got a child with a puppy, and the mass of the child is 20 kilograms, and the mass of the puppy is 5 kilograms. They're going to go to a park, and they're going to climb to the top of a slide that I've shown down here. A couple things I want to point out about this slide is that C is at the same plane as the bottom of the ladder. So we're not going to have a disparity of height when we get to C. When the kiddo and the puppy slide down the slide, they're going to end up on the ground. B is going to be halfway up the slide. Now, I want to kind of talk through a couple of things because we were going to determine work a couple of different ways. One, we're going to determine the work that it takes to get both the child and the puppy to the top of the slide. And then we want to look at the work that it just takes to get to the puppy to the top of the slide. And this is one of those tricky things that we get in our online homework, that sometimes the way they ask the question is a little bit different. And then we want to determine the speed of the child and the puppy at points A, B, and C. So let's look at the work first. Remember that work is related to, and depending on which class you're in and depending on which book we're dealing with, work is going to be related to the force that's along the same line of action as the distance in which we're going. Now, for some of you, that means it's a dot product. And for some of you, that means that we show that force times distance times the cosine of the angle, trying to get that force in line with the distance that we're moving. But for most of us, and a lot of the time, we're going to apply our force in the most efficient way, and that's going to have us get that force to go along the same line of action. So if I'm taking myself up to the top of the slide, the force that I'm going to have to do is I'm going straight up the top of the slide, and that's the force that I'm going to apply. So in this case, what is the force that we're applying? Well, we're having to overcome gravity to get from the bottom of the slide to the top of the slide so we can figure out that force. Of course, the distance is just how high did we go. And so in this case, it's going to be 1.5 meters. So we remember we're looking at that force along that line of action that we're having to do. So we're having to overcome gravity. So let's look at what we have to do. So we're going to overcome gravity. And if I'm looking at just the child, that's 20 kilograms times 9.81 to get my weight. Remember, mass times gravity is going to give me weight, and weight is a force. If I'm looking at just the puppy, it's going to be 5 kilograms times my 9.81 meters per second squared, and I'm going to get that 49 newtons. And if I'm combined, I'm going to get the combined action is going to be 245 newtons, which is going to get me to the top of the slide. Now, a newton, remember, is a kilogram meter per second squared. So the work to get to the top of the slide is going to be the force that we have to overcome. If I'm doing both the child and the puppy, I'm going to do 245 newtons. That's the force that's being applied, and it's going to be 1.5 meters to get to the top. Multiply that together, and I'm going to get 368 newton meters. And newton meters in this case is going to be defined as a new unit. It's a unit of energy, and that's going to be called a joule, and it's a unit of energy, and that's where we're going to use it. We're going to use the letter J. Now remember, we had those two different questions, that question about where we got the child and the puppy to the top of the slide, or if we were just looking at the puppy to get the puppy to the top of the slide. Just the puppy, I'm going to do the 49 newtons times the 1.5 meters, and I'm going to get the 73.5 joules. But now we want to look at that energy part. Now remember that energy is defined as the ability to do work. So to get to the top of the slide, we're going to use that work energy theorem to get us there. So the work is going to equal the same amount of energy that we put into the system. So at the top of the slide, we've got our work that we put into the system, or we've added energy into the system. So now we're going to look at what the conservation of energy says. So conservation of energy is going to tell us that the energy at the top has got to equal the energy at the middle of the slide, that's got to equal the energy at the bottom of the slide. Or the total energy at the top equals total energy halfway down the slide equals total energy at the bottom of the slide. So we get that conservation of energy. Our work energy theorem says the work that we put into it is also going to allow me to figure out how much energy I have in the system. Okay? Now, in your book and in your text and in some of the other lecture videos, we talk about the potential energies being that energies, particularly if we're talking about the potential energy due to gravity, it's that energy that we've used to get me to a height h, or look at what we have here, that force, remember the force was the weight, mg, h is the height, mgh gives me my potential energy or my energy of position. So the work that I did is equal to the potential energy. Work conservation, the work energy theorem says the total energy at the top is now equal to the work that I've done in. And at the very top, we're not in motion yet. Okay, at the very top, we're not in motion. Remember that you saw it in your book and in the other lecture videos that kinetic energy is equal to 1/2 v or 1/2 mv squared because I have that energy of motion. And I'm just going to put that in here for reference because this is a good conceptual kind of a problem to think about. I could have energies related to a spring, which is equal to 1/2 the spring constant times its displacement squared. Or I could have heat, light, sound, and other types of energy that I might have to incorporate. But that energy of the spring and those other energies, I don't have to deal with it in this particular problem. I just am kind of bringing that in to think about what kind of our total energies that we have. So we can look at what's happening at the very top, all right? At the very top, the total energy, because we don't have a spring, we're not worried about heat, we're not worried about light, we're not worried about sound, we're not worried about those other things. The total energy at the top is going to be the sum of all the energies, which in this case is just my kinetic energy and my potential energy. But at the very top, based on what we've seen before, I have no motion. If I have no motion, V is equal to 0. I have no kinetic energy. So at the very top, I have my total energy is equal to my potential energy, which is equal to the work that I put into the system. So here it's equal to the work done. I'm going to do my 25 kilograms times my 9.81 meters per second squared times my 1.5 meters. And lo and behold, I've done 368 joules of work, no kinetic energy. So we could have answered one of those questions just by looking at the problem, right? You could have answered at the very top, I have no motion, therefore I'm at 0. So now let's go to the bottom. We know what our energy is, and at the bottom, we've got a little bit different here, so let's go get all that into the picture. At the bottom, I've got potential energy plus kinetic energy, but at the bottom, I have no height, right? C is at the same point as where I started. So H is going to equal to 0, so everything's related back to my kinetic energy. We can rearrange the equation and we can solve for the velocity. And at the very bottom of the slide, the kiddo and the puppy are going to slide down and they're going to be at 5.93 meters per second. Now I want you to think about this for a second. I want you to kind of, here's a thought problem to look at. If I were to do this same problem using my kinematics equations, and I'm looking at the speed after which I've dropped the ball, am I going to get the same answer? Something for you to think about. Now, let's look at halfway down the slide. Well, this time I have both kinetic energy and potential energy, but I start out with the same total energy that I've had all the way around. I know halfway down the slide that H is equal to 0.75 meters, so now I can go in and apply my problems, rearrange and solve for the velocity, and see that the velocity is now 3.84 meters per second. So hopefully this problem and thinking through this problem and looking at the various spots throughout the problem is going to help you out looking at the work conservation theorems, the conservation of energy theorems, and you'll see some other examples.